Hello, my name is Alegra Martinez Vasquez, and today I'm going to be presenting my oral exposition of the problem situation in the subject of statistic analysis. So, first, we were given a problem situation that consisted that a used car dealer wants to predict the selling prices and future sales of a Camaro brand car, and for this, we were provided with data on various factors affecting this car price. And the factors are the age, the mileage condition, which means how long has it been used, and the ownership history, how many owners has it had um, along the years. And we were provided this for us to develop a predictive model for future sales. So we began with exploratory data analysis to understand the relationship between the variables. Here we can see two scatter plots showing price versus age and price versus mileage. And as you can see, both plots indicate a negative correlation. That's why they are downwards. This suggests that as the car age or mileage increases, its price tends to decrease as well. This intuitive result sets the stage for a regression analysis, and just as I said before, um, if the car uh, keeps on aging and the mileage keeps on increasing, the price is going to be decreasing. Next, we did a regression analysis in age and mileage. Um, so we applied a linear regression to quantify the relationship between the price and predictors, age and mileage, and the regression model showed an 81.12% accuracy in predicting the car prices, indicating a strong fit. However, the residual analysis suggested that a negative exponential model might better capture the decreasing trend of prices in age and mileage. Okay, as I just said all the previous things, we stepped into a challenge which was the inclusion of categorical variables. So these two categorical values were the car's condition and ownership history. The problem with these variables is that they weren't numeric variables. So it had like this a bit of a challenge in the problem situation. But as in the model we were using, it didn't require categorical variables. We recommended using an encoding technique just like dummy variables to convert categorical variables into numerical variables so we can better suit the regression analysis. Um, and yes. Okay, so then we started like the strong part of the problem situation, which was forecasting the models for the the for the future sales in the Camaro brand selling or the future sales of the brand. So we first used the moving average model. As you can see, the estimation of the number of cars that will be sold next year, um, it's performed by using a moving average model with a window of 2. While it goes closer to the true values, its predictors remain constant and fail to capture the cyclical nature of the sales data, resulting in high prediction errors according to the MAP, which in this case was 43.5437. Then we used an exponential smoothing model, and um, this model also failed to account for the cyclical patterns in the data, leading to straight line predictions. That did not reflect the actual sale trends. just as it can be seen in the graph and in the table. After that, we then applied a linear regression to predict future sales, and this model performed better, showing a slow increase in quarterly sales values each year, as it can be seen. But however, it still had significant errors due to not fully capturing the cyclical nature. So, after that, we introduced the hot winters additive model, which better accounted for the seasonal variation in the sale data. As you can see, this model showed improved the prediction accuracy compared to the previous methods. The smoothing constant helped us to adjust the model accordingly and reduce the error presented in the map values. But because of the increasing nature of the sales, this additive version does not represent this side of the behavior in the data. As we can observe in the graphs and in the map values, the smoothing constant for zero point 0.4 was the one who achieved the least amount of error at 31.7322 map. So we are able to trust that its predictions come to be the most accurate to the real values of the next year. If we plot together the graphs, as you can see in the top right corner of the presentation, we can better understand this point. As we can visualize the model closest to the data, the rail line model with 0.2 smoothing constant. The green line is a model with 0.3 smoothing constant, and the pink line is a model with zero point 0.4 smoothing constant, as it can be seen again in the graph that is in the right top corner. And finally, we applied the Holt Winters multiplicative model, which is suitable for data with both trend and multiplicative seasonality. This model showed the highest accuracy with mean absolute percentage error, also named MAPE, of 24.21%, making it the best fit of our sales prediction task, as it can be seen both in the table and the graph. Even though in the first year of the graphs are further away, as the years pass, they become more accurate and precise, especially in the case of the model with zero point 0.4 smoothing constant, which is shown by the pink line in the top right corner of the presentation. So it isn't wrong to assume that for the following year it will also come closer to the data. And finally, we have the graph with all the methods. And by this, we can conclude that the best one is the winter multiplicative method. And the reason for this is that we obtained, as you said before, a 24.2117 MAPE, which means it is most accurate because it indicates a relatively lower error rate compared to other methods evaluated um, uh, um, throughout the presentation. And a winter multiplicative method calculates exponentially smooth values. Also, this one is the best for data with trend and with seasonality that increases over time. Um, just as the graph is representing. So, um, this was everything for this problem situation, and thank you.